Hey class, this is Professor Sweeting, and this is going to be the first online lecture of the semester. We're going to pick up where we left off before test 2, and that is with the transportation problem. Um, so we'll be studying this problem for the remainder of this week and all of next week. Um, and you will be expected to take a quiz, which will be made available tomorrow. Um, this quiz, it's not going to cover this material in depth, and is just meant as sort of like an introduction to the new format of this course. So I'll post more about that in an announcement, um, either today or tomorrow. So today is meaning Wednesday. So just keep an eye out for that. So anyway, I guess I just also want to say I hope you all are doing well and staying safe in this time. And it's rather unfortunate that the class has to be carried out in this way, but you have to be adaptive. So, all right, so I'm going to get started. So the transportation problem. So for this problem, we're trying to distribute products from a number of source locations, so you can think of warehouses or distribution centers, to a number of destination locations, which you can think of as stores. So each source will have its own unique supply, and each destination will have its own unique demand. So for simplicity, we assume there's only one type of product resource being transported. So in real life situations, you may have numerous products coming from numerous uh, distribution centers. So that's just a reduction that just makes this problem easier for us to study. All right, so the cost to ship from a source to a location will vary. So, and by location here, I mean destination. So this might be due to certain factors such as distance or terrain between them. Our goal is to find the most cost-efficient shipping policy, that is to say, determine how much of said product each source should send to each destination so that the demand of each destination is fulfilled, the supply of each source isn't exceeded, and the total shipping cost is minimal. So that's a very wordy introduction to this type of problem. Here's a particular example. Suppose we have 3 Apple stores in Hamilton County which need to stock up on the new 2020 MacBook Air ahead of its release. Stores 1 and 2 are located in relatively low traffic areas and thus require only 40 and 50 MacBooks, respectively. Store 3 is located in a busy mall and therefore requires 60 MacBooks. So, as we can see in this problem, each of the destination locations has its own unique demand, right? Its own unique requirement for the product. So in this case, the product are the MacBooks, right? And so Apple has 3 distribution centers in Ohio, which have in stock 70, 30, and 50 MacBooks respectively. So these are the source locations, and each of them has their own supply capacity. All right, and then in addition to this, the cost per MacBook to ship from each destination to each, from each source to each destination varies. How so? Well, the cost per MacBook to ship from Center 1 to each store, so store 1, 2, and 3, is $2, $4, and $2 respectively, while the cost per MacBook to ship from Distribution Center 2 to each store is $3. Lastly, the cost per MacBook to ship from Center 3 to each store is $1, $2, and $3. So the idea behind the transportation problem is how much of the product each source location should send to each destination location. All right, so I'd just like to note here another reduction being made, or another assumption being made about the problem. Right, here we see that the number of stores is the same as the number of, so those are the destination locations, is the same as the number of source locations, right, the distribution centers. So that just makes things easier in the application of our algorithms. And also the total demand, which is the sum of the demands of the stores, is the exact same as the total supply, which is the sum of the supply at each distribution center. Okay, so this is a lot of information. What do we do with this information? Like, how do we begin to solve the transportation problem? Well, we need some kind of representation. So, as we had seen in the postman problem and also the traveling salesman problem, we had a diagram that we were able to analyze and apply, algorithms to find or to solve certain management problems, to solve those management problems. So we're going to look at two diagrams that are used for studying the transportation problem, right? So these diagrams are going to encode all of the relevant information of that transportation problem. So the first is a type of graph, right? It's a weighted graph with weights on both the vertices and edges. It's also directed, and it's called the network model, right? So the vertices of the network model are the distribution centers, so which we'll denote by D1, D2, D3. So these are also the source locations, right? So not D as in destination, but D as in distribution. So these are the source locations. These are the locations that we're shipping from. And then we also have vertices for each store, so where we're shipping to. Okay? So I said this was a weighted graph, and we have weights on both the vertices and edges. Well, what are the weights for the vertices? So for those vertices that represent source locations, the weight is the supply of that particular source, right, of that warehouse or of that distribution center. So D1 will be distribution center 1, D2 distribution center 2, so on. So in this problem, distribution center 1 has as its supply 70 MacBook Pros, MacBook Airs. So we put that as the weight of the vertex. Distribution center 2 has 30, and distribution center 3 has 50 MacBook Airs. All right, and for the weights of the vertices that represent destination locations, or stores, S is here for store, right? The weight will be the demand, right? How much of the product is required for that particular destination, right? Or that particular store. So in this problem, store 1 requires 40 MacBooks, store 2 requires 50 MacBooks, and store 3 requires 60 MacBooks. Right, so we've represented so far in this model via weights on vertices the destination locations, right, the stores, and the source locations, or the warehouses, and their capacities and their requirements. Okay, so I'm not sure if I said this already, but another simplification of this problem, right, is that the total demand equals the total supply. I think I did say that, all right? So that'll be the case in all of our problems because it makes the application of some of the algorithms that we're going to look at much easier, right? So then what we do is we add edges from a distribution center to a store based on whether or not we can ship from that distribution center to that store. So another simplification for this problem is that we're assuming every distribution center can ship to every store. All right, so that may not always be the case. Okay, so let's do that. So we draw an arrow from each distribution center to each store. Okay, and then the weight of that edge, right? So that arrow is an edge, and the weight of that edge is the cost of shipping per item from this source to this destination. So it costs, right, to ship per MacBook from destination or distribution center 1 to store 1, $2. That's here, right? Okay. It costs $4 to ship from distribution center 1 to store 2, and $2 to ship from distribution center 1 to store 3. We then do the same for the remaining distribution centers. Okay, so distribution center 2, right? It costs $3 to ship from this distribution center to all of the stores. and then lastly for distribution center 3. It costs $1 to ship to store 1 from distribution center 3, $2 to ship to store 2 from distribution center 3, and $3 to ship to store 3 from distribution center 3. So in this graph, right, it's a weighted directed graph. Doesn't necessarily need to be directed. Since it's directed, we don't have to make a distinction between the vertices that are source locations and the vertices that are destination locations, because the arrow indicates that relationship, right? But in this case, if you didn't have the arrows, if this wasn't a directed graph, then by making a distinction in the labeling of the vertices, you can denote that information. We're doing both here. All right, but in any case, with this network model, we're incorporating all of the relevant information from this problem, right? So who needs what and how much it costs to send from one place to the next, right? Okay, so another representation is given by a table which we call a tableau, all right? So here's the table. It consists of a number of rows and a number of columns, all right? So each column corresponds to a source location or distribution center, and each row corresponds to a store or a destination location. All right, so how do we incorporate the information from a transportation problem in such a diagram? Well, okay, here's the problem again. This is a separate page. The information about shipping costs goes in these upper left-hand corner boxes. All right, so the value that would go in this upper left-hand box would be the cost of shipping an item from this distribution center to this store. So in this case, the cost to ship from a MacBook Pro from distribution center 2 to store 1 is 3. So it's actually the same. So it was 3 to ship from distribution center 2 to store 2, and 3 to ship from distribution center 2 to store 3. Okay? All right, so what goes in this upper left-hand corner box is the cost to ship from this distribution center, right, of the column to this store. So in all of these tableaus, we'll adopt the convention that the distribution centers correspond to the columns and the stores correspond to the rows. All right. Okay, so let's fill in the rest of this shipping information, right? Shipping costs. So distribution center 1 to store 1 is 2. Distribution center 1 to store 2 costs 4 and 2, and then lastly 1, 2, and 3. So we filled out all information about shipping costs. Now we need to fill in information about demand. What is the demand and what is the supply? So we use this column, right, to store the demand of the store of that particular row. Okay, so in this particular cell, we put the demand of the store to which that row corresponds. All right. So in this case, the demand of store 1 is 40 MacBooks. Right? The demand of store 2 is 50 MacBooks, and the demand of store 3 is 60 MacBooks. Right? And then in this row, in these cells, we put the supply corresponding to the distribution center or source location of that column. So distribution center 1 has a supply of 70 MacBooks. Distribution center 2 has a supply of 30, and distribution center 3 has a supply of 50. Right? And here we just put the total of the two, which is or the total of that row, or this column, which should be the same, and it's 150. Okay, so as you can see, we've included all relevant information of the transportation problem in this table. So, all right, solving a transportation problem amounts to filling in this tableau, right? So in this cell, we'll put how many of that product distribution center 1 should send to store 1. So in this portion of the cell, and vice versa, and the same holds for all of these other cells. So the value a cell holds outside of this box will be the number of the product that this distribution center, right, of that column should send to this supply. right? And then you can take so for example, if we put a 3 here, right, that would imply that distribution center 2 should send 3 MacBook Airs to store 3, right? That's not necessarily what our solution will be, but that just should illustrate to you what goes in this cell. And if we put a 10, a 3, and a 10, right? I'm writing lightly, hopefully you guys can see, because I need to erase this. The total, right, the sum of these values of these cells is the total number of that product that this distribution center sent out. And this should not exceed, right? So when we fill this out and we have a shipping policy, this should not exceed, the sum of this column should not exceed this value here, right? Because this is the total supply of that distribution center. Similarly, the sum of the values of a particular row, right, correspond to the total supply, right, that this store of that row is being given, right? So in this case, we have that store 3 is getting 10 units of the MacBook Air from distribution center 1, 10 from distribution center 2, and 10 from distribution center 3. So that does not meet the total demand or the required demand of that store. So a valid shipping policy should have columns whose sum of values do not exceed this value. So we call these rim conditions. So this rim condition, which corresponds to the supply of the distribution center in that column. And similarly, and that should hold for all columns, and similarly we should have that the sum of the values of any given row should be equal to the rim condition of that row, the corresponding rim condition of that row, right? So in this case, that doesn't hold. So that would be a valid shipping policy. So if we filled out this tableau with values, the cells of this tableau with values, then those two conditions should hold for that shipping. That would constitute a shipping policy, and those two conditions should hold for it to be a valid shipping policy. So how do we find what is the cost of a shipping policy? So we're talking about finding an optimal shipping policy, which means one that has minimal cost. So what is the cost? The cost is essentially, so if we had something like this, I don't know. I'm just arbitrarily filling this out here. Okay, so 50, 30, and then he has 70, so he needs to produce 60. So this is an arbitrarily decided shipping policy, which is valid because the sum here doesn't exceed, this meets the demand for each row, and then the sum of the values in the columns don't exceed the available supply, or these rim conditions. So this is a valid shipping policy. So how do we find out how much this shipping policy costs? Well, we compute a sum. So we shipped 10 MacBook Airs from distribution center 1 to store 1 at a cost of $2 per MacBook Air. So that would be $20. And then we add to that, $3 times 20 MacBook Airs plus $10 times $1, 10 times 3 is 30, and we sum that up. I guess I'll just do it. 80 plus 120 is 200. This is 100, 320. So this was the total shipping for this, or the total shipping cost for this shipping policy is $320. So that's how we extract the shipping cost, or the total cost of a shipping policy from the tableau. So that'll be relevant later. Alright, so the tableau and network model can be used to represent the same kinds of problems as we saw, right? But each lends itself better to certain algorithms. So we'll begin our study of the transportation problem using tableaus, right? And algorithms that use the tableau structure. Right, so we filled in the one with information of the previous example, and we've talked about some of the problems. So I'm going to conclude this video here. I just want to note that the first few algorithms, like I said, will deal with tableaus, and then I think sometime next week we'll deal with algorithms that use the network model which are a little more complicated than those that use the Tableau. So in the next video, I'm going to discuss the first algorithm for finding a shipping policy, which is called the Northwest Corner Method.